Hello, and welcome to a video lecture for Civil Engineering and Mechanical Engineering 501. We have been talking about curved beams in our recent discussions and lectures. We're going to continue this video lecture by talking about the correction factors when we have I-beams and T-beams or any curved beam with a thin web and flanges. Large errors can develop when computing the circumferential stress in these situations. And these errors develop because of the radial forces that develop when the flanges deflect. As we talked about, these flanges down here in this I-beam essentially act like cantilever beams and induce bending stresses of their own in a sigma x direction and not the theta direction that are the critical stresses for the curved beam analysis. So the result of having a thin web with flanges is that these stresses get magnified significantly in the flange where it connects to the web. And it's these stresses that we want to discuss. There's a method known as Blaiks correction factor that addresses this issue. And essentially what it does is it converts the original I-beam or flanged thin web beam to a beam that would compare to that actual I-beam when the stresses were computed. So using Blaiks method, the actual maximum circumferential stresses are accounted for by converting the original model to a corrected model that will allow the actual stresses to be computed. And you can see what essentially happens in this I-beam here. Here's the center of curvature, and we're mainly interested in this inner flange because that's where the stresses will be the largest. And you can see that due to Blaiks correction, this inner flange has been significantly reduced. Then when we compute the stresses in this reduced flange, we'll get the actual values that exist in the beam. If we were to use the conventional sigma theta theta equation on the original beam, our stresses would be in air due to the bending that occurs in the flanges. When we use the Blaik corrected I-beam, the stresses will now have the correct values. It's important here that we understand all the terms and that we can refer to these to this nomenclature. This BP is the projecting width of one of the flanges as shown. So that's from the edge of the web out to the edge of the flange. R bar is for double flanged beams. And you can see that we have an R bar outer and an R bar inner, and those values go to the center of the flange. TF is the thickness of the flange, and TW is the thickness of the web. BP prime for double flange beams is given as BP inner and BP outer, or we can use alpha BP, and this alpha is given by this ratio of BP squared, which is this projecting width of the flange, divided by R bar times the thickness of the flange. And we'll compute that so you see an example of how to do it. But it's important that we get these values right because alpha is an important quantity for us. And then B prime is equal to this 2BP prime plus TW. And it's the reduced width of the new flange. That's the value that we're looking for here. It's important that we review this paragraph here. It says, when the curved beam equation is applied to an undistorted cross-section that has been corrected by BP or B prime, it predicts the maximum circumferential stress in the actual cross-section. And this maximum stress at the center of is at the center of the inner flange. And because of the bending of the flanges, this transverse stress sigma xx develops, and the stress state is now a two-dimensional stress state with a sigma theta theta and a sigma xx. And the sign of sigma xx is opposite to sigma theta theta. And so Blake gave the following approximation for the sigma xx stress for the inner flange. And what you do is on the next page here, you compute the sigma xx stress by computing negative beta times sigma theta theta. And this beta is obtained from a table which is determined by this ratio that we just computed, BP squared over RTF. And the sigma theta theta is the magnitude of the circumferential stress at the mid-thickness of the inner flange. And the value of sigma theta theta is computed based on the corrected cross-section. And then we'll compute the shear in these beams, and the maximum shear, as we know, can be computed by the radius of the Mohr circle, and this can be computed by taking the maximum stress minus the minimum stress and dividing that quantity by 2. So let's look at an example of how we can do this. In this example problem, we have a T-beam that is our curved beam. And the center of curvature lies 40 millimeters from the flange. So here's our center of curvature, 40 millimeters to the inside of the flange. If the curved beam is subjected to a positive bending moment of mx is 2.5 kilonewton meters, we're asked to determine the stresses at the inner radii and the outer radii. So in here at 40 millimeters and then out here at 100. And we're to use Blake's correction factor and then compute the maximum shear stress. So given the original dimensions here, the first thing we want to do is compute the ratio of BP squared over RT. And our BP was this distance on the flange, and so we can see that that's given here as 15. R is the distance to the center of the first flange. And so that's our 45, and then T is the thickness of the first flange, which is this 10. So this gives us our ratio. From table 9.3 then on page 341, we can get alpha and beta. Then we can come and compute BP1, and with BP1 we get alpha BP, turns out to be 13.2 millimeters. And so we can compute our corrected flange width, BP prime. Then we can compute A1, R1, and A sub M1, and A2, R2, and A sub M2 using the combined equations for when we have multiple cross sections or multiple bodies that we're going to combine. And this would be the total A sub M, and total R that would be used in our original sigma theta theta equation. So based on our new geometry then here that we got by using Blake's correction quantities, we're now able to come and compute the stresses. And so to compute those stresses, we just go to the sigma theta theta equation, and we'll go to point B, and our moment was given. We computed our new total area. Our R would be to the point of interest at B, which is the inside, so it's the 40. Then we have our A sub M, and again our values down here. We can see that we compute a tensile stress, and that makes sense because we have a positive moment. Then we compute our sigma theta theta at point C, and we get a negative stress. That's on the outer wall, which makes sense that these two are opposite sign. Then we can come down and compute our theta XX max by beta sigma theta theta bar. And it's important that the sigma theta theta bar is the mid inner flange as to where we compute the stress. So the R mid inner flange is 45. We need to make sure that we use our total A sub m, our A, and again our R mid inner flange. And that's where this sigma theta theta bar comes that we use to compute the sigma XX and get a minus 197.3. And then we can compute our tau max, which is the difference of our max and min normal stresses divided by 2, and we get our 224.5. So this is the level of problem I would expect you to be able to do in your homework and on an exam. You'd certainly have the equations available to you, but you would need to understand the process of how to get the alpha and beta terms from the table and how to use those values to compute these stresses. This is where we will end our discussion of curved beams. We will not talk about the deflection of curved beams, and we will not talk about curved beams going plastic. So you do not need to work any homework problems associated with deflection of curved beams or plastically deforming curved beams or plastic moments associated with curved beams. Just work the problems up through these Blake's correction factor problems. Thank you. Hello, and welcome to a 501 lecture about beams on elastic foundations. These types of beams are found throughout all kinds of applications and problems. We can see some examples here. For example, your spine could be treated as a beam in a tissue or a soft foundation. Oftentimes we'll put, or doctors will insert medical devices such as shown here. There are some springs and a plate with some screws attached to bones in the recreation of a pelvis structure. And oftentimes these parts can be modeled as beams on elastic foundations. Much larger structures, such as bridges, we can have the bridge that is supported by all these cables, essentially is on a spring or an elastic foundation. Again, we have a footing, a foundation part, component of a structure on a soil foundation. Here we have railroad tracks, and these railroad tracks are certainly on a soft soil foundation. And so there are many, many applications of beams on elastic foundations. And it's important that we understand how the stresses are distributed through the beams under these conditions. And so with that introduction, we'll go ahead and start talking about the theory behind these types of systems. In our analysis, we're going to use the well-known Winkler model to look at the beams on elastic foundations. The assumptions behind the Winkler model are that the foundation resists the loads transmitted by the beam. The deflection of the foundation is linear, so we're going to treat it kind of as linear springs. The stresses in the beam and the foundation obey Hooke's law, and we are going to assume small displacements, which means we stay in the linear region. A little more about the definition of the Winkler model. It's in this foundation model, it's assumed that the elastic beam is placed on an elastic foundation and that applied loads pass through the beam to the foundation. The foundation responds linearly elastically, which means the pressure developed at any point between the beam and the foundation is proportional to the deflection of the beam at that point. And this model works well as long as the deflections are small and in the linear region. In the figure here, a beam that is infinitely long is shown to be mounted on an elastic foundation. There's a point load P placed at the origin O, and it causes the beam to deflect. And you can see that this point load on the beam then corresponds to a distributed load by the elastic foundation. So the elastic foundation does not reciprocate to the point load by applying a point load, but a distributed load is applied. And this distributed load, or this distributed force, is called Q, and it has units of force per unit length. And so here is our Q, which has units of force per unit length. Based on the given coordinate system, positive beam deflections are downward in the positive y direction. So note that y here in our geometry is going down, positive. And the origin is at the centroid of the infinitely long beam. A positive displacement is downwards and causes Q to push back up on the beam. Therefore, Q is positive when it's pushing up. And when the deflection is upward, tension is produced in the supporting medium and it pulls down on the beam, and so Q is negative. You can see here this would be the deflection. Here is the slope. Here is our bending moment, and here is our shear. Now we can compute these values using these equations here. So from the geometry and a differential element, we can write these derivative terms. Theta is simply the slope, and it's the change in the deflection with respect to z, or dy dz. Mx is the second of y with respect to z squared, with the ei in front, where I is the moment of inertia, area moment, and E is the modulus of elasticity. Then we have the shear force, or the shear, Vy, is the third derivative, and we have Q is actually the fourth derivative. So theta is, again, the angular rotation. It's due to the applied load. The minus sign in these equations comes because a positive applied load causes a negative reaction moment and force. So that's why those negatives appear in those equations. For elastic foundations, the distributed load Q can be written in similar form as the spring equation, F equals Kx. Here we would write Q equals Ky. And this K is often written as Bk naught, where B is a uniform beam width, and is the width of the beam, and it has units of length. And then K naught is called the modulus of the foundation, or subgrade modulus, and it has units of force per length cubed, where K has units of length times force over length cubed, or force per length squared. So it gets a little confusing as to which one you're talking about, whether you're talking about K or K naught. Oftentimes K naught is the value in the table if you have lookup values, and so if it's in a table, we'll often look up K naught values. As shown down here in this copy of a table 10.1 in your book, it tells us a soil type, and then it gives us a range of K naught values. Sometimes the best way to determine which K you're talking about is simply by the units. And so if we're looking at K naught, we'll have force per length cubed. If we're looking at K, we'll have units of force per length squared. Now, if we take the expression Q equals KY and substitute it into the definition of Q on the previous page, where we had the fourth order derivative of Y with respect to Z, we can write this differential equation. And the solution to this differential equation is given by this expression here, where we have these C1, 2, 3, and 4, which are constants of integration, and then we have e to the beta z, and sine beta z, cos beta z, and so forth, where beta then turns out to be k over 4eix raised to the 1/4 power. And this expression up here for y, again, is the displacement of the beam, and it represents the general displacement or the solution to the displacement equation for an infinitely long beam supported on an elastic foundation with a point force or a concentrated lateral force in the middle of the beam. So now to solve this equation right here, we need to apply the boundary conditions. As can be seen, we have 4 constants, and so we need 4 boundary conditions, and you will always have 2 boundary conditions on each end of the beam. And so we will have 2 different cases, two beam configurations that we'll look at when determining the boundary conditions, and we'll use the solutions to those 2 boundary conditions to solve most all the problems that we will be looking at. The first configuration that we're going to look at is an infinite beam loaded with a point load in the middle. This is the one that we've just been looking at. So here's my z value. My origin is 0 here in the middle. Y is going down, point force, and an infinitely long beam on the foundation. The second beam configuration that we will look at is a semi-infinite beam, so it's only infinite in one direction, and it's loaded with a force P and a moment at the 0 end of the beam. So in either case, in case 1 we have an infinite beam, and in case 2 we have a semi-infinite beam, the y deflection of the beam goes to 0 as z increases. And that's why we look at these infinite configurations, is because we want that deflection to go to 0 in our solutions. And because of this, the constants of integration, C1 and C2, must be 0, because we have e to the beta z, and for large z, those would become extremely large quantities. So based on the infinite beam configuration that we're going to use, which essentially forces our beam displacement to go to 0 at one end, we can eliminate the coefficients C1 and C2, and our expression for our displacement can be given here as this equation, as shown, where we have e to the minus beta x, or beta z. And this makes a lot of sense. What it physically represents is that your beam on your elastic foundation has to be long enough that the ends of the beam do not see deflection. So for a railroad track, for example, when the train was on the railroad track, the track would have to be long enough that it would have a 0 deflection out away from the train. And if it was shorter than that, then we would have to, we'll see what we can do. If it's too short, there's some corrections that we have to apply. But the basic theory is that the deflection, that the beam is long enough that the deflection goes to 0 away from the load. And that's what lets those 2 coefficients go to 0. Now let's look at what happens to the other 2 C values for the 2 conditions. So our first condition again was the infinite beam subjected to a concentrated load. And because of symmetry, the slope of the beam directly under the point of the load is 0. And so we know that the change in y with respect to z is equal to 0 for z equal to 0, which gives us this boundary condition here. Then for half of the load P, it must be carried by the elastic foundation on the left of Z, and on the other half, it must be carried by the right of Z. So this can be expressed as the integral of ky dz is equal to P over 2. So I'm integrating on the positive side, 0 to infinity, and I'm saying that the integral of that elastic force foundation part is equal to half of the applied load. So the foundation shown here has to carry, the foundation on the positive Z side here has to carry half of the load. And that's kind of what we're saying with that equation there. Now applying these two boundary conditions gives us dy dz. These are quite easy derivatives to take. If you recall, when you take the derivative of an exponent, the coefficient just comes down in front, and so we'd have minus beta e to the beta z, and then we have the rest of this would follow as shown here, and we evaluate this at z equals 0. So my cosine terms become 1, my sine terms go away, and I can see that C3 has to equal C4, which could equal some other constant. And now I can plug this in, and my equation looks like this, and I can apply this last condition that we came to on the previous page, and we can see that C is going to be equal to P beta over 2K. And this becomes a critical equation. We'll actually use this coefficient quite a bit in some continuing some equations that will be coming here shortly. So the final equation that we have for the deflection for this beam is P beta over 2K e to the minus beta z, and then these trig terms. And this is all for z greater than 0. However, because of the symmetry, we know we won't use negative z values. We can just put in positive z values and flip the sign. So this works great for the displacement. For theta z, when we want to look at the slope, we can compute this equation by P beta squared over K B beta z. And then for the mx, we have a C beta z, and for Vy, we have a D beta z. And this A, B, and C, and D beta z are given by these terms here. And so what we basically will do is, if I want to know the displacement, I will come down here and compute the A beta z. Then I would bring that up into this equation and apply the P beta over 2K to compute the actual number. And the reason why we've done that is because tables for these terms here can be made and plots made so that we don't have to always compute these values. And these tables or values for these quantities here are shown in tables 10.2 on page 362 in your book, and you can see those on this next page. If we jump ahead, here is table 10.2. So for a specific beta z value, you could come down and pull off the A beta z, B beta c, beta z, and so forth, and get all the values there. And then those values are what's computed here, and you can go get your stress, your slope, your shear, or your moment, whichever quantity you're looking at. Now, one thing we want to be careful with here, based on the symmetry, is the displacement is simply completely symmetric. However, the slope is not, it changes, so a theta of a negative z is equal to a negative theta z. The moment then again is symmetric, and again then the shear is like the slope, where the v minus z is equal to a minus vz. And again we saw that these tables where we can look these values up. I kind of actually like this plot and find it very useful, where here we have beta z going along the horizontal x-axis, and then we have the coefficient a, b, c, and d plotted on this vertical axis. And these terms are normalized, so the maximum value is 1. The thing that's kind of interesting here is where these quantities are maximum values and where they cross 0 values. So we'll talk about that a little bit. It's noted that the A essentially represents the displacement, and so we see that we cross this 0 at 3 pi over 4 is where that crossing is for the A, and so that any beams longer than that could be treated as having that 0 displacement from then on out, because it has 0 deflection at that point, and that's where our boundary condition was. So the total length of the beam would be 3 pi over 2 beta, and then we would have 3 pi over 4 on each end of each side of the beam. The infinite length beam can be modeled with these same equations using this, and the above equations may be used as long as there's at least this 3 pi over 4 beta from the point the load to either end of the beam is met. Now if we look at the beam that is semi-infinite with a moment and a point load applied here on this end and then semi-infinite in this direction, we can solve for the boundary conditions C3 and C4. By doing that, this would be the boundary condition on the moment. So at z equals 0, our second derivative would be equal to the negative of the moment. Our third derivative would be equal to the force. And solving for those conditions, we'd get C3 and C4 is equal to this. And our differential equation solution, then after applying the 4 constants of integration, would be given as this expression. And the nice thing about this is we can express the displacement, the slope, the moment, and the shear, just like we did before, but in terms of different quantities. So this is the same D and C and A and B that we used in the previous equations for the infinite beam, but now when we use the semi-infinite beam, we see that our displacement is given as a function of the D terms and the C terms, and our theta is given by the A terms and the D terms, where in the previous equations, this displacement was just given by the A terms and the B terms and so forth. But to use those same coefficients, we need to now use these equations here on the semi-infinitely long beam. Seldom in problems do you simply have one single force applied. Oftentimes there are multiple forces and distributed loads. And so we need to look at using superposition to combine the effects of these loads to get the total result. So for an example problem, we're given an infinitely long beam here. We have an origin right here. We have a point A located at a distance ZA from the origin, and we have a point B located a distance ZB from the origin going to the left. We have 3 point forces, P1, P2, and P3 applied on this infinite beam, and we want to find the displacement at point A and the rotation or slope at point A due to these 3 loads. So when I look at this, I go back to my equation for my infinite beam, and I'll have beta over 2k, and then I start to look at P1, and I have to compute the right A beta z for where the P1 load is applied. And it's important that we remember that Z is the distance from the applied force P to the point of interest. So using that definition, I come to my point, my P1, and I look at the distance from the applied force P1 to the point of interest A, and that would be a ZA distance, which is this distance here, plus A, which is this distance, to give me the total combined distance of A plus ZA. Now for force 2, I would go ZA plus this distance B. And then for point 3 or load 3, I'd have ZA plus the C distance. And I'd have essentially the same thing down here for the theta. Now let's look at point B, where point B actually lies between points P or loads P2 and P3. And we want to make sure that we're able to get the right distances for point B. To do this and get the right distances, we're going to take ZA as a negative number and then add C, B, and A to that as appropriate. And so this will give a negative Z for ZA plus C, for example, because ZA would be negative and it's a larger quantity than C according to the figure. So in the case of negative numbers, you need to make sure that you take the absolute value and then switch the signs when you're dealing with theta and V, as we talked about. When we're looking at the displacement in the moment, it's symmetric and we can just use the same sign. So YB then would be beta over 2K P1, and we'd have A sub beta, and then we'd go ZB plus A. And again, this would be for force 1, and we would have the ZB plus the A distance, and that would give us this distance here based on that minus sign. We'd do a similar thing for P2. We'd have ZB to get us to here, and then we would have B, and that would give us about the right value here. And then on the third force, we'd have ZB plus C, but we have to take the absolute value of this quantity in order to get the right value. And that's because C is not as big as the value of ZB. So hopefully this helps show how to use superposition in these types of problems. Let's finish by looking at an example problem and kind of put all of this together. So it says here that a heavy machine has a mass of 60,000 kilograms. Its mass center is equidistant from each of 4 ground supports located at the 4 corners of a square 1.5 millimeters on a side. Before it's moved to a permanent location, temporary support must be designed to hold the machine on a level horizontal surface on the ground. And the surface layer of the ground is silt above a thick layer of inorganic clay. And by the theory of soil mechanics, it's estimated that the spring constant of the soil is K0, K0 of 0.029 newtons per millimeter cubed. And the machine is placed centrally on 2 long timber beams. And these beams are 200 millimeters wide and 300 millimeters deep. And the beams are parallel to one another with centers 1.5 meters apart. And we're asked to determine the maximum deflection of the beams, the maximum flexural stress in the beams, and minimum required length L for the beams in order for this to take place. So basically what we've got to do is store this large heavy cart on a couple of beams that are sitting on the soil. And we want to make sure that these beams can't carry the stress as well as the elastic foundation can carry the stress, and that neither of those will cause a failure. So to start the problem, we can look at from table 10.2, page 362, and figure 10.3 on page 363. The maximum deflection and the moment occur where A and C equal 1. And we can see that from this figure here. Coming back to the plot of those coefficients, we see that the maximum values occur for the A, the B, and, or excuse me, the A, the D, and the C all occur at beta Z equal 0. Note here that this maximum occurs in the slope at a non-zero beta Z. But we know that for this case it will be at Z equals 0. So coming back to this problem, we know that the maximum deflection will occur directly under one of the supports or in the middle between the two supports. And that's kind of what we need to figure out. So we can put an origin here and we can determine where that will occur. So putting my origin there under wheel 1, I have y1 is equal to p beta over 2k. Here's my superposition. I have a 1, and then I have a beta z1. My moment would be a p over 4 beta 1, and then my superposition c beta z1. And now I need to compute beta. And beta is given by this k over 4 EIX to the quarter power. K would be given by this expression here, where I was given K naught. Then I have BH cubed over 12, and I can write this expression here for my I. Beta then becomes this quantity here. Now I can look under the wheel at Z equal 1, and I can get beta Z1 turns out to be this, my A beta Z1, and these come from my tables, and I can get those values, and I can compute those based on the equations. Then under one wheel, I have y1, m1, and theta 1 given by these expressions that I had on the previous page. And I can look at the center of the two wheels, and when I do that, my z would take on a value of 750. So I'd have a beta 750, and here's my A beta of 750 and my C beta of 750. And then at the center of the two wheels, my superposition changes. I'd have a A beta 750 and an A beta of a minus 750, where I'd have the two offset from each other. My center would be at the origin, and this is the Y that I would get and the moment. And so I can note that the deflection is largest at the center between the two wheels, and the moment is the largest under one of the wheels. And I see that by comparing this 14.5 millimeters for the center deflection under in the middle to this 13.27, and I compare the 44.5 kilonewton meters to the 21.1. So that's what lets me make this final conclusion. And then to compute the length of the beam that I would need, I can just simply add the length of the cart and then our ground rule of 3 pi over 2b or 2 beta. I get this, and so the length has to be greater than 81 or 8.1 meters. So this is kind of an example of how we use superposition at 2 points. Hopefully this is helpful to you, and we'll be able to address any questions that you may have in our next class. Thanks for watching.